Hi students, today's class is about Unit 4 Multiple Integrals, Concept, Applications of Double Integrals, Areas, both Cartesian and Polar System. Contents, Objective and Outcome, Area in Cartesian Coordinates, Area in Polar Coordinates, and Applications. Objective and Outcome. The objective is applications of double integrals, areas, and outcome will be student get to understand how double integrals are used to find the areas. Area in Cartesian coordinates. Let the curves AB and CD be y1 is f1 of x and y2 is f2 of x. So it is the figure, rough sketch region. AB is the curve, that is y1 is f1 of x. Another curve is CD is y2 is f2 of x. The region bounded by the two curves and the two lines x equal to a line and x equal to b line, which are parallel to y axis. So this is the closed region. Here we have to find out the area. These curves are known as Cartesian curves. Now we have to find out the area. For this we have to take the strip. The strip is generally drawn parallel to y-axis in the closed region. According to strip, we can compute y limits. The lower part of the strip touches to the curve AB. Thus we will have y1 is f1 of x, and the upper part of the strip touches to the curve CD, that is y2 is f2 of x. Thus y limits are obtained. Y limits are must and should be in terms of x, that is y varies as y1 to y2. Now x limits must and should be constants. These constants are obtained from the ordinates, that is x equal to a and x equal to b, because x equal to a line intersect the x-axis at a0 and x equal to b line is intersects the x-axis at b0. In this closed region, x varies as a to b. Thus, x limits are obtained. X limits must and should be constants. So, y limits are y1 to y2 and x limits are a to b. And we have a small particle whose area is delta x and into delta y. Now using double integral, we can compute the required total area of the closed region, that is which gives area is integral a to b integral y1 to y2 dx dy. Here the integrand functional value must and should be 1. So area formula is double integral dx dy is the required area for the Cartesian curves. Don't forget the formula. To find the area of a given closed region, just we have to compute double integral with integrand function as 1 and order is dx dy. Just we have to compute the limits of the double integral and then we have to evaluate the double integral, which gives the required area for Cartesian coordinates. Not only for Cartesian coordinates, we can compute the area for polar curves also. Next concept, area in polar coordinates. To find the area of the polar curve r equal to f of theta between the radius vectors theta equal to theta 1 and theta equal to theta 2. It is noted that the area of an element is r delta theta. So it is the rough sketch of the region. Theta equal to theta 1, theta equal to theta 2 are the radius vectors. O is the pole point. R equal to f of theta is a given polar curve. To find the area, we require R and theta limits. R limits are R varies as 0 to f of theta because the pole point having radius 0 and the highest value of R is f of theta. So here we have to take the small strip which is rotating in between theta 1 to theta 2. That is theta equal to theta 1, theta equal to theta 2 are the radii vectors. So that theta varies as here theta 1 to theta 2. Here we noted that the area of an element, this element, small element is r delta r into delta theta. Now compute to total area, we have to compute double integral. That is the required area is given by integral theta equal to theta 1 to theta equal to theta 2, integral r equal to 0 to r is equal to f of theta, r delta theta. In Cartesian coordinates, we will have dx dy. Here in polar coordinates, we have r delta theta or r dr d theta, where r is also known as the Jacobian's coefficient. So it is the required area in polar coordinates. Thus, to evaluate the area in Cartesian coordinates, we have area is a double integral dx dy. But in polar coordinates, area formula is double integral or dr d theta. Now, applications of double integrals. Problem. Find the area bounded by the parabola y square equal to 4ax and its lattice rectum. So it is the rough sketch of the region. It is y square equal to 4ax parabola symmetrical about x-axis and passing through origin. Y-axis is tangent at the origin. So it is the parabola y square equal to 4ax or y equal to root of 4ax. It is a lattice rectum, that is LL dash, which passing through the focus point, that is S A0. Y equal to 0 means x-axis, x equal to a line which is parallel to y-axis. Now we have to find out the area bounded by the parabola and the lattice rectum. That is the shaded area we have to find out. For this we require the limits of the double integral. To find the limits, we have to take the strip. It is the strip which is drawn parallel to y-axis. So according to strip, we have y limits are y equal to 0 because the strip lower part touches to the x-axis. So y equal to 0 because x-axis equation is y equal to 0. And the upper part of the strip touches to the curve, that is y square equal to 4ax. Thus we will have y equal to root of 4ax. Thus y limits are obtained. And x limits should be origin 0 0 and another ordinate is a0 as vertices. So here x varies as 0 to a. So required area is 2 into area ASL. Just we have to double the area because the area is symmetrical about x-axis. The area above the x-axis is lies on the same area below the x-axis. So that we have to multiply here 2. Don't forget, we have to compute the total area which is occupied or bounded with the parabola and the lattice rectum. Just the half area is multiplied with 2 to get the total area. So that is 2 into x limits 0 to a and y limits 0 to root of 4ax. But what is the value of root 4? 2. That is 2 root ax dy dx. Here first we have to integrate with respect to y and then x because y limits are variable limits in terms of x. Integral of 1 dy is y. Substituting upper limit we will have 2 root ax and lower limit 0. that is 2 root ax minus 0 is 2 root ax. Now clearly double integration sum is reduces as a single integration. Here 2 root a is constant, just take it to the outside, that is 2 into 2 root a is 4 root a is constant. Now x power 1 by 2 integration is x power 1 by 2 plus 1 by 1 by 2 plus 1, that is x power 3 by 2 by 3 by 2, limits 0 to a. Substituting upper limit and then lower limit as 0, we will get, and simplifying we will get the result as 8a square by 3. So it is the required area of the parabola y square equal to 4ax and its latus rectum, that is LL dash. Another problem, find the area between the parabolas y square equal to 4ax and x square equal to 4ay. So here we have to find out area between these two parabolas. So it is the rough sketch of the region. Both the curves y square equal to 4ax and x square equal to 4ay. Both are intersect at origin O00 and another point is 4a, 4a. So it is the rough sketch of the region. Here the shaded area we have to find out. For this we have to take the strip. So these two are the equations 1 and 2 given curves. Now on solving 1 and 2 we will get the intersecting point, that is a 4a, 4a. Area formula is double integral dx dy. Now we need the limits of the double integration. So double integration limits are according to strip x varies as the left part of the strip touches to the curve y square equal to 4ax. Here x is y square by 4a, and the right part of the strip touches to the curve. The curve is x square equal to 4ay, in that x is root of 4ay. So that the limits of x are obtained, x limits are in terms of y. Once again, the left part of the strip touches to the curve y square equal to 4ax, in that x is y square by 4a, and the right part of the strip touches to the curve x square equal to 4ay, in that x is root of 4ay. Thus x limits are obtained in terms of y, and y limits should be constants. Origin O00 and another intersecting point or another point on the y-axis in this closed region is 0, 4a. So we are having 2 points on y-axis, origin 0, 0 and another point is 0, 4a. Here clearly y varies as in these 2 points 0 to 4a. Thus y limits are obtained, y limits must and should be constants. So we have to take the limits according to this region. So clearly y varies as 0 to 4a and x varies as y square by 4a to 2 root or 2 root ay or root of 4ay. Now we have to compute this double integration. For this we have to take the integration first with respect to x and then y. What is the integration for 1 with respect to x? X. Limits are y square by 4a to 2 root of 4ay or 2 root ay. Substituting upper limit as root of 4ay minus lower limit y square by 4a. Simplifying and then integrating with respect to y. Root of 4a is constant. Root y integration, that is y power 1 by 2 integration, is y power 3 by 2 by 3 by 2. Minus 1 by 4a constant. Y square integration is y cube by 3, that is y cube by 3 into 4a is 12a. Now we have to replace the upper limit as a 4a and lower limit as 0. Substituting upper limit and then lower limit and then simplifying, we will get the result as 32a square minus 16a square is 16a square by 3 is the LCM. So it is the required area of the given bounded of the two parabolas. So two parabolas are y square equal to 4ax and x square equal to 4ay. So simply we can find the required area. Just we have to take the limits of the double integral. For this, we have to take a strip which is parallel to x-axis. The left part of the strip touches to the parabola y square equal to 4ax. Here x varies as y square by 4a. And the right part of the strip touches to the parabola x square equal to 4ay. In that x is root of 4ay. Thus x limits are obtained, variable limits. Now y limits must and should be constants. So y limits are 0 to 4a. So using these limits, we can evaluate the double integral with the integrand function as 1. Integrand function is 1. Another problem. Evaluate double integral over a r square sine theta d theta dr over the area of the chordioid r equal to a into 1 plus cos theta above the initial line. So here the problem is related to polar coordinates, and the given curve is polar curve, that is r equal to a into 1 plus cos theta. We have to find out the area above the initial line. Solution: the region of integration A can be covered by radial strips whose ends are at r equal to 0 and r equal to a into 1 plus cos theta. The rough sketch of the region is like this. It is the cardioid. X-axis is nothing but theta equal to 0 initial line. Y-axis is nothing but pole line, that is theta equal to pi by 2 line. Negative x-axis is nothing but theta equal to pi line, and the shaded region area is above the cardioid. So in this area we have to find out double integral value. For this we need r theta limits. Here r theta limits to get, we have to take a point p of r comma theta on the curve. So it is the polar point, that is p of r comma theta. Here r limits can be taken as r equal to 0, that is the radial strip whose end is at r equal to 0, and r equal to a into 1 plus cos theta, that is about the curve. So r moves from 0 to a into 1 plus cos theta. And in this closed region, that is the shaded region, the theta, the radii vector moves as theta equal to 0 to theta equal to pi. So the limits of theta are obtained. Theta limits should be 0 to pi. Only we have to take above the initial line part. Only we have to take the upper half of the cardioid. For the upper half of the cardioid, theta moves as 0 to pi, and r limits as, from pole point we have to consider r limits. From pole we will have r is 0. For the curve we will have r is a into 1 plus cos theta. So whenever we will have r theta limits, now we can compute the required double integral. So the strip lies between theta equal to 0 and theta equal to pi. Thus the required double integral, just we have to take the limits. First we have to integrate with respect to r and then theta. While integrating with respect to r, keep theta as constant. That is sin theta is keep it as a constant, that is keep it as a silent. R square integration with respect to r. But what is the r square integration with respect to r? R cube by 3. Just we have to replace upper limit as a into 1 plus cos theta and lower limit as 0. So substituting upper limit and then lower limit as a 0. Now taking out the constant, now we have to integrate this. So this can be written in cos power 7 theta by 2 into sin theta by 2 d theta, because 1 plus cos theta means 2 cos square theta by 2. 2 cos square theta by 2 whole cube, that is a 2 cube 8. Cos square theta by 2 whole cube is cos power 6 theta by 2. But sin theta can be written as 2 sin theta by 2 cos theta by 2. Just taking out the constant, we will have 2 into 8 is 16. And cos power 6 theta by 2 into cos theta by 2 is cos power 7 theta by 2 and sin theta by 2. So it is the simplification. Just we have to know about two formulas. The two formulas are 1 plus cos theta is 2 cos square theta by 2 and sin theta formula is 2 sin theta by 2 cos theta by 2. Now we have to replace theta by 2 equal to some another variable phi. Now we have to change the limits and then we will compute. So limits are also changed here and then computing, so that we will have 16 by 3 into a cube minus cos power 8 phi by 8 limits 0 to pi by 2, because cos phi derivative, what is the derivative of cos phi with respect to phi? Minus sin phi. So only sin phi is there. Just we have to take a minus as inner of the integral and minus as the outer integral. Now we have a known formula. The formula is integral of f of x whole power n into f dash of x dx is f of x whole power n plus 1 by n plus 1. So using the formula cos power 7. So 7 plus 1 is 8 whole by 7 plus 1 8. So required result is negative cos power 8 or 5 by 8. So once again we are using the formula here, integral of f of x whole power n into f dash of x dx is f of x whole power n plus 1 whole by n plus 1. Here f of x is cos phi and f dash of x is negative sin phi. N is 7. So negative cos power 7 plus 1 5, that is 8 phi whole by 7 plus 1, that is 8. Now we have to replace upper limit as pi by 2 and then lower limit as 0. So substituting the limits and then simplifying, we will get the result is 4 by 3 a cube. So it is the required result of the double integration. Now another problem, find by double integration the area lying inside the cardioid and outside the circle are equal to A. So it is the cardioid and the circle. Cardioid clearly meets theta equal to 0, theta equal to pi by 2, theta equal to pi and theta equal to 3 pi by 2. So we can draw the rough sketch of the region. So simply by taking the intersection points, just we have to take the theta values and then we have to compute the r values, so that the rough sketch is taken by easily. And we will have a circle radius r equal to a, that is a center at a pole and having radius as a units. So it is the rough sketch of the region, but we have to find out the area lying inside the cardioid, and outside the circle, the shaded area or dark area we have to find out. For this we need r limits and theta limits. So clearly r varies as here in this closed region, in this shaded region r varies as a into 1 plus cos theta, that is the circle to curve, circle to cardioid, that is a into 1 plus cos theta are r limits. So clearly here the required area is A, B, C, D, A, A, B, C, D, A, B, C, D, A. So it is the shaded area, that is which is obtained by 2 into area of A, B, D, A. Only we are finding here the upper half of the cardioid area and then which is multiplied with 2, because the whole region is symmetrical about initial line, that is theta equal to 0 line. The curve is symmetrical about, the region is symmetrical about initial line, so that we can compute only the area of ABDA which is multiplied with 2. So r varies as here a to a into 1 plus cos theta. For the above the part, theta varies as clearly here theta equal to 0 to only pi by 2. Don't take theta as a pi. Here only we have to find out in first quadrant area, that is theta moves as 0 to pi by 2. The upper half of the part area is multiplied with 2 because twice area is there. The curve, the whole region is symmetrical about initial line. Now we have to evaluate this double integral with respect to r first and then theta, because r limits are variable limits in terms of theta. Now r integration is r square by 2. Substituting the upper limit as a into 1 plus cos theta and then lower limit as a, and we have to take out the common as a. So that is a square into 1 plus cos theta whole square by 2 minus a square by 2. Clearly here 2 get cancelled, and then taking out a square as common. Now simplifying, that is 1 plus cos theta whole square is look like a plus b whole square, that is a square plus 2ab plus b square. That is 1 square is 1 cos square theta plus 2 cos theta. Clearly here 1 get cancelled. So we will have cos square theta plus 2 cos theta. Now can evaluating the single integration, that is cos square theta can be written as 1 plus cos 2 theta by 2, and then 2 cos theta integration is 2 sin theta, and then substituting the upper limit as pi by 2 and lower limit as 0, we will get the result as constant. So it is the required area of the chordioid inside the area lying inside the chordioid and outside of the circle. So easily we can obtain, just we have to take the limits of r and theta. Here we are only taking the limits for r and theta above the region, and the result is multiplied with 2 because the curve is symmetrical about the line theta equal to 0. Symmetrical means the total area is divided into two equal parts by the line theta equal to 0 here. So simplifying the answer. Now another problem, write down the double integral to find the area between the circles. Solution: r equal to 2 sin theta is a circle with a diameter 2, that is radius is 1 unit. R equal to 4 sin theta is a circle with a diameter 4, that means the radius is 2 units. So these are the shapes of the curve, that is r equal to 2 sin theta is a circle P, and r equal to 4 sin theta is a circle Q, and the dotted area is the shaded area is the required area. This area we have to find out, that is the area between the circles. So that's the required area of the integral 0 2 sin theta to 4 sin theta, because r moves as 2 sin theta to 4 sin theta and theta moves as 0 to pi. So first we have to integrate with respect to r and then theta to get the required area of the given region. So r equal to 2 sin theta and r equal to 4 sin theta, the shapes of the curves are obtained by putting theta values and getting r values, and the intersection points are of the form r theta. So easily we can draw the rough sketch. X-axis is nothing but theta equal to 0, y-axis is nothing but theta equal to pi by 2, and negative x-axis is nothing but theta equal to pi. Put theta equal to 0, theta equal to pi by 2 and theta equal to pi, we will get r values, and using intersection points we can draw the rough sketch of the region. So easily we have learned in already in intermediate how to draw the rough sketch of the region. So clearly we can draw the rough sketch of the regions, and we have to evaluate this closed region. So for this closed region, r moves as 2 sin theta to 4 sin theta and theta moves as 0 to pi. Now we have to evaluate this double integration first with respect to r. But what is the integration for r? R square by 2. Substituting upper limit as 4 sin theta and then lower limit as 2 sin theta. 4 sin theta whole square is 16 sin square theta by 2 minus 2 sin theta whole square is 4 sin square theta by 2. Now evaluating the single integration, Double integration is now becomes a single integration. 6 is constant, but sine square theta integrate can be written as 1 minus cos 2 theta whole by 2. Suppose there is cos square theta, then it can be written as 1 plus cos 2 theta whole by 2. So since there is a sine square theta, we can write 1 minus cos 2 theta by 2. Now half is a constant, just taking out the half. 6 by 2 is 3, 1 minus cos 2 theta. 1 integration with respect to theta is theta. Cos 2 theta integration is sin 2 theta by 2. Substituting upper limit pi and then lower limit 0. So pi minus sin 2 pi by 2, but sin 2 pi value 0. Sin 0, sin pi, sin 2 pi, sin 3 pi and so on are 0. So substituting lower limit is 0, the total value is 0. That is 0 minus sin 2 into 0. Sin 0 by 2 is 0. That is 3 into pi is 3 pi. So it is the required area is 3 pi of the region, required area of the region. Another problem, evaluate double integral r cube dr d theta over the area bounded between the circles r equal to 2 cos theta and r equal to 4 cos theta. Solution, given region is two circles r equal to 2 cos theta having radius 1 units, r equal to 4 cos theta having radius 2 units. It is the rough sketch of the region. The first one is r equal to 2 cos theta curve and second one is r equal to 4 cos theta. Now we have to evaluate the area between the circles. Between the circles, that means 2 cos theta to 4 cos theta. What are the r limits? 2 cos theta to 4 cos theta. And this area, according to this area, the radii vector which moves from theta equal to negative pi by 2 to positive pi by 2, that is y dash axis, negative y axis to positive y axis. But here we are taking polar coordinates, thus theta moves from negative pi by 2 to positive pi by 2. Thus the theta limits are obtained. Theta limits merchant should be constants, r limits are merchant should be in terms of theta. So clearly in between the circles, r moves as a 2 cos theta to 4 cos theta, and theta moves as a negative pi by 2 to positive pi by 2. Now we can evaluate easily the double integration. Only we have to compute or determine the limits, and then the result will be obtained easily by evaluating the double integration. Now given some, let it be equation 3. Now using the limits negative pi by 2 to positive pi by 2 as outer limits of the integrand, and the inner integral limits are r limits, that is 2 cos theta to 4 cos theta. First we have to integrate with respect to r and then theta, but r cube integration is r power 4 by 4. Substituting upper limit as 4 cos theta and the lower limit as 2 cos theta. So we'll get, substituting upper limit as 4 cos theta and lower limit as 2 cos theta, we will get like this. And then simplifying, and we will have cos power 4 theta is an even function, because while replacing theta with minus theta, the function do not changes. That is cos power 4 theta cannot changes when theta is replaced with minus theta. So cos power 4 theta is an even function, so that we can write negative pi by 2 to positive pi by 2 limits as 2 into 0 to pi by 2. So 2 into 0 to pi by 2, and then simplifying we will get like this. Now we can evaluate 0 to pi by 2 cos power n theta d theta. What is n here? N is 4. So evaluating this, we will have n minus 1 by n into n minus 3 by n minus 2 and so on into 1 by 2 into pi by 2 whenever n is even. So using the formula, so substituting here, so that is 3 by 4, 1 by 2, pi by 2, and then simplifying, we will get the result as the constant, that is 45 pi by 2. It is the required result. So it is about applications of double integrals. Using double integrals, we will find areas for both the curves, that is Cartesian curves and polar curves. For any queries or doubts or clarification, please contact. Thank you.